So, hi everyone. It's my pleasure to introduce the final guest speaker in our course, Aakanksha Chowdhery. She is a senior staff research scientist at Meta. She has been a lead researcher in pre-training of large language models such as Palm and Gemini. She led the 540 billion Palm model at Google and was a core member of the Gemini Pathways, Palm E, and MedPalm projects. Before Google, she led interdisciplinary teams at Microsoft Research and Princeton University across machine learning, distributed systems, and networking. Recently, she's experimenting with agentic workflows in open llama models at Meta. She completed a PhD in electrical engineering from Stanford University and was awarded the Paul Marconi Young Scholar Award for outstanding scientific contributions in her dissertation. That welcome again, Aakanksha, and you can take it from there.
Thank you again for inviting me. Just wanted to confirm you can hear me clearly.
Yes, we can all hear you.
Awesome. Thank you. Again, thanks for inviting me. And it's a privilege to present the work on large language models, specifically on multimodal reasoning and its applications. I'll cover two domains, robotics and computer use. And please note that I'm presenting the work done with many, many collaborators. A lot of this work was done at Google, across Google DeepMind and Google Research, and more recently with collaborators at Meta. And for some of the recent work that I've been doing in computer use, I am presenting the work of peers because my own work is unpublished, but I thought it would be interesting for you to get a sense of the basics in this field, given that it's very timely right now. So let's start with just the basics of what I'll be covering. I'll start with examples of multimodal reasoning and how these examples seem very promising. Then we will cover some of the applications that we have tried in robotics with Palm E, one of the works that we did previously. And then we will cover some of the applications in computer use that has become more popular recently. So let's take a look at what it means to have multimodal reasoning in a model. So last year in December, Gemini was released, and more recently, Llama models and Pixtral models have showcased that they are natively multimodal. What it means to be natively multimodal here is that the models can reason seamlessly over sequences of text and image that are interleaved, oftentimes often having the capability that they can also generate images. They can reason over interleaved images in video. They can reason over interleaved text, image, and code, and they can even add audio to the mix. Though there have been questions whether these models can really see things within an image, so there have been questions whether they can do any spatial reasoning. So let's take a look at each of these and what it means for these models to be natively multimodal. So in December last year and an updated report in February this year, in the Gemini technical report, the first example that is presented is one where you're verifying, where the model is asked to verify the student solution. Now, all of you have amazing TAs and faculty who spend a lot of time grading your problems. However, the models can always help. So here, the model is prompted with verifying the student solution in a domain of physics. On the left, what you're seeing is a skier is sliding down a frictionless slope, and the model is asked to verify the solution that the student has generated. It's a handwritten note, and it's also asked to correct the student solution if it is incorrect. On the right, you see the model response, and the model response shows that the model is not only able to recognize the handwritten content, it is also able to verify the student response, and then it finds that there is a small correction, and in terms of how the student is assuming what is the correct height, and then it goes ahead and corrects that and provides the correct solution. Now, this is incredibly promising in that sense that the models can intricately reason over interleaved sequences of text, which is the request that we have made for the model, and the image of the student solution. And if you had multiple such sequences, you can imagine a lot of different applications. Now, another example that is presented in the Gemini technical report is one where the model is prompted in a one-shot setting over, again, interleaved sequences of images and text. However, this time it also has to generate images. So what you're seeing on the left is that the model is asked to make creative suggestions. It is given two colors, blue and yellow yarn, and then it's basically asked to give two ideas of what one could do with these two colors and the yarn. And the model is given examples like it could come up with a cute blue cat or a blue dog with a yellow ear. And then it's asked, okay, now I have two yarn colors, pink and green, and it's supposed to generate creative suggestions. And on the right, it comes up with very nice suggestions around, oh, how about a green avocado with pink seed? Or how about a green bunny with pink ears? So this gives you a sense of applications where you're not just limited to understanding images, you can also generate images in many cases. And you're not just limited to understanding single images. In this particular case, the model is prompted with a YouTube video of football or soccer penalty that is missed. And the model, and here the prompt is showing a sample set of 4 images from that video, but obviously the model is prompted with many more images from that video. And as the model gets the input of the video, the model is asked, how could this person improve their technique? And what is interesting in the model response is that the model is able to give some recommendations around how the foot is not making contact with the ball, and how the person could perhaps kick the ball differently or position the ball differently, which sort of suggests that the model is able to analyze some of the temporal dependency across videos and come back with some sense of what is happening, which is quite interesting. And we're not just limited to text and images. Here is another example where we are able to add audio to the mix. So the Gemini technical report presents this example where the model is able to reason across text, image, and audio, where what is happening is that in a conversational setting, the user is inputting an interleaved set of images and talking to the model. So it's asking in the first set with this particular image, with the first image, these are the ingredients that are available, and what is the first step to make a vegetarian omelet? The model analyzes that and gives the first step, and then interestingly, the user presents a first image of having tried that first step and asks for whether it is ready now, and the model is able to analyze and say, oh, it looks almost ready, but what are the next steps that you should take? And then advises and so on. So this kind of gives you a sense of, okay, we're not just limited to text and image, we can do audio. And more recently, you've seen some popular applications of Notebook LM, which really pushes the voice applications of using text and audio further in real world use cases where you can ingest large amounts of text and present them in terms of podcast, really reducing the amount of time it takes for you to say listen to content that is complex or really long. And another fun aspect is that why restrict to just audio? Why not just put code in the mix? So another example from Gemini technical report is that you can interleave text, image, and code. So the model is prompted with 4 plots and asked to rearrange the plots here from Matplotlib. I'm sure many of you have to do such data analysis tasks, and you've done some plotting in Matplotlib. And based on the instructions, I will not make you go through the entire prompt, but basically the model is required to rearrange these plots. And based on the instructions, on the right, the model is generating some code and analyzing what these plots mean. And then it is re-rendering a new plot. So it is able to understand what is inside these plots, how that plot might have been rendered, and then it's able to re-render the plot. So the re-rendered plots is able to move from the bottom right. There is this parabola that is colorful to the top left, and the top left images moves one over, and similarly, you can observe the images in the bottom row. So it's fascinating that, and particularly mind-blowing, that the model is able to reason across code, image, and text as a modality. And this really starts to show up in interesting, useful ways where you have to do, for example, data analysis tasks. Now, a lot of these examples are just the first signs of things kind of starting to work, but what does it really take to build these models? Now, unfortunately, with the closed source models, there is absolutely no information, and Gemini Technical Report is not able to share any details. So we can learn a little bit more from open source side of things. So we know that these models are trained across internet scale data sets of images and text, which possibly allows them to seamlessly combine and reason across modalities. They also add audio and code in the mix. Pixtral in particular says a little bit more about how they train their models across image and text. So we can take a look at what might be happening. So it shows that in terms of architecture, it is using a vision encoder that is projecting into a transformer decoder. So the vision encoder tokenizes the images. So you have these pixtral vision transformer, and then there's a projector, and you get these multimodal tokens, which then are doing the next word prediction given a sequence of text and images. So here you have to say cat, this is a cat, and then there's a dog, and each of these are basically getting projected into this decoder, which is then saying, okay, this is a dog. So this is your one-shot example of just image captioning. And it is able to take an arbitrary number of images as input. And some interesting aspects that are worth highlighting if you look at the architecture that Pixtral presents is that it is able to natively support variable image sizes. Why does variable image size matter? Because like if you have a really big chart or a really big document, then you need to be able to handle that size. Other interesting aspect in this particular architecture that they present is the rope 2D encodings, which facilitate these variable image sizes. So they say that the way they have designed the rope 2D encodings is by enabling them to have a relative property. So there's basically relative difference in height and position that is all that matters in these position embeddings for vision, and not the absolute position. So both of these seem like important properties that we will need in computer use cases and in robotics use cases where you will need to have better scene understanding. And another interesting aspect of handling these variable image sizes is really demonstrated in this particular figure, which analyzes the performance of the model relative to prior existing vision encoders. So let's take a look at that. So clip A is trained as a vision encoder, which is just vision transformer, the large one, with L on 224 pixel size, and then green one is on 1000 or like 1120 pixel size. Typically, what traditional encoders, vision transformers are trained on is like ImageNet, where the images are broken down into tiles, and then when you feed these tiles the of 224 by 224 or 336 by 336, this is essentially what the vision encoders are taking as input. Now, what Pixtral does is that it basically allows you to adapt to both high and low resolution by doing some random crops and feeding them as the input. And it allows the model to handle both high and low resolutions at their native aspect ratio. Now, and this, as you see in chart QA, gives a big boost in performance in dog vision. So chart QA is a benchmark which basically does question answering over charts. And another example in analyzing documents and answering questions over documents, again, it gives a big boost. In visual question answering over just general benchmark, you kind of get very similar performance. And another benchmark in AI 2D, you get similar performance, but in the where it matters that you need to have variable image sizes, it really makes a difference. So that gives you some sense of like what these models might be doing. Now, another important point that has been brought up in several evaluations this year is the question that do these models really see and understand the images? I mean, it's great that I said, okay, there seems to be multimodal reasoning, but is there spatial reasoning in these models? So these are some figures from a paper, What's Up with Visual Language Models, and questioning their spatial reasoning capabilities. And I am showing you 4 images here. In each of those images, you have a dog and a table. And a human, as a human, you would be easily able to see, okay, the dog is on the table, or dog is left of the table, or the dog is right of a table, or a dog is under the table. But the models kind of struggle with this in some cases where the left and right, or whether the dog is on the table or the under the table is not that clear to them. And this paper in particular makes the hypothesis that in the training data sets, prepositions are rare, ambiguous, and the captions that are provided with images don't have enough detail for these models to be able to spatially reason. And then they propose fixes along the lines of generating a better data set, or having loss objectives that can kind of handle these examples better. So having contrastive or hard negative examples and so on. So that's an interesting set of challenges that these models face. However, my colleagues from robotics side of things presented a paper called Spatial VLM in CVPR this year, where they do claim that we can endow these models with spatial reasoning capabilities by constructing the right data sets. And they claim that the lack of this spatial knowledge is because of training data. So here, what they're showing is that we have an image. On the top image, you have basically an image from a house, and the model is prompted to answer, can you determine if the pots are closer to the viewer or the chairs are closer to the viewer? And in the bottom image, the model is prompted to determine the relative distance between the player and the man in black. And what the models do with this relative positioning information can be a struggle. So they construct special data sets that allow the model to learn about relative distances and positioning. And after doing that data set intervention, they showcase promising examples where the model does have the ability to show some spatial reasoning capabilities. So in particular, this example is quite interesting. What the model is prompted with is there is a blue Coke can, an orange can, and a silver 7-Up can. And the model is asked if they will roughly form an isosceles triangle, roughly being that the shortest and longest triangle edges is less than 0.1 meters. And in terms of multi-hop reasoning steps, what the authors show is that they analyze the distance between blue Coke can and orange can, the distance between orange can and silver 7-Up can, and the distance between blue Coke can and silver 7-Up can. And they analyze all of these distances, and then they are able to, and the model is then able to like take these distances and basically say, okay, yeah, I can reason across the distances that I've analyzed, and it roughly forms an isosceles triangle, which seems very promising, and which also gives us promise that, okay, now these models can be used in applications such as robotics and computer use, where the relative localization of these models or the distance between objects will matter. Okay. Quick question. Do we take questions in between, or we just keep going with the talk? Okay, I'm not hearing a response, so we keep going. Okay, so we move to the second part of our talk, where we will talk about a few applications in robotics. And I know the talk was advertised as applications in computer use. We'll get there, but we have published work on the robotics side, so that's I'm going to talk about it first. Um, Here I'm going to present a published work called PALM-E, which is an embodied multimodal language model that was built on top of PALM, and it combines a vision encoder with PALM to endow the model with single model that can do embodied robotic tasks, vision language tasks, and across multiple robot uh, environments, and reason across them. So this was actually one of the first tasks where we saw promising results in long horizon planning performance. So let's take a very simple environment where the model is required to learn, or is prompted to figure out how to move this yellow block, which is under the orange block, on top of the blue plate. And the model needs to come up with an answer. For example, in green on the right, we show an answer. Now, one of the big challenges of understanding this is that how should the image be represented for the model to reason about this particular scenario? So one possibility is that you could give a spatial description like this. There are two blocks in this image, which are right next to a green plate, and then there's a blue plate, and then the orange block is on top of the yellow block. However, what you might have a challenge if you just give a scene description in text is that it might be very task dependent, so it might not be actionable, and oftentimes you might not have enough fine-grained details there. This is one example where you have a lot of information in the image, and to provide a generic actionable scene description might be incredibly hard. We can simplify this by just learning an encoder, perhaps, that learns the information from the image or the scene and feeds it to the language model. So that could possibly work, as we were seeing in our previous examples from vision language models. Even when we know that, there's still a question of, should we feed raw pixels of the image into this encoder? Should we input 3D neural scene representations into this encoder, or should we input states into this encoder? And that's one research question that has been answered in several research works more recently, with different set of results on different benchmarks. In robotics, we go with a simplified assumption where we are just feeding the image in raw pixels to the encoder. And in PALM-E, when we inject this multimodal information, we are inputting it as interleaved sequences of images and text into the large language model. So you have a text embedding, and you have the vision encoder tokenizing the raw pixels. And based on the example here, where you are inputting an image with these blocks on a table, you're prompting the model with how to grasp, say, for example, the white object. The model will output the action in the token space. Now, a very interesting aspect of this particular line of work that is worth noting is how much data do we need for the model to learn these capabilities? Because data collection in robotics is incredibly a lot of work. So one of the research questions that PALM-E answered was that if you scale up the model size, both on the large language model sides, and these sizes are for the original PALM model, and you scale up both the vision transformer, and you feed it a lot of data. So like you basically give it all the robotic data, and you also train jointly with visual question answering tasks, that is the internet scale data, will we get transfer. Now, transfer here means that by learning from all the data on internet scale tasks like visual question answering, image captioning data that exists, for example, in ImageNet or COCO data sets or much larger data sets, will we be able to solve problems on the robotics tasks? And we do find positive results that I'm going to describe in the next few slides. And we also observe that scaling up the model size in this particular case gave us emergent capabilities around multimodal chain of thought and multi-image reasoning, and it also minimized catastrophic forgetting in some ways. And just this is a published paper in ICML last year. So this is basically presenting what was the training data that was used for PALM-E, where only 10% of the data was robotics data, and the rest of the data was essentially internet scale, visual question answering, and captioning data sets, some of which were repeated to get enough data for PALM-E to be trained. So let's take a look at some of the results, and we're going to present the results in 3 environments. The first environment will be task and motion planning, as you see on the first image, where you are basically the robot has to place these blocks based on the task that the model is assigned. This one is only in simulation. The second image will be for language table environment, which is both in simulation and real world. This is showing you that it's a much more complex environment where there are blocks of many colors. And the third environment will be basically fractal robots, which are instructed to do real world tasks, such as fetching a bag of chips or fetching cans. And this work was done in SayCan, which is in Google Robotics. And the results of training this model showed that we could get a single checkpoint that can generalize across several environments and get promising results in closed loop end-to-end planning or even long horizon tasks. And a single checkpoint could generalize across many of these different environments and even show promising results on the zero-shot setting for these tasks. And what is really happening in this case when I'm showing you these promising results is that PALM-E is basically getting a long horizon goal. So in the language table environment, you have a lot of these colored blocks, and the model is getting an instruction such as sort the blocks by color. So it is supposed to sort the blocks by color, and it will generate these language commands. And there's another model which is basically converting it to a set of actions. So the planning is happening at a 1 Hertz time scale, while there's a smaller model which is moving much faster and converting that policy into robot actions. And then you're getting a feedback loop of robotic images, which then feeds back into PALM-E, which corrects what is the next set of language commands that need to be generated. So on the right, there is an example of this where it is being asked to do a task, and it's basically showing you some example. If I match it correctly, it's possible that I put the, okay, so don't look at the task 1 aspect, but basically it's sorting the blocks by color and it's generating these language commands, and an action policy is essentially actuating that with the robot. And then based on the feedback, it is doing a replanning step. One interesting thing to remember here is that you can generate this in a single model, which was done in a later work called RTX, but this is just simpler to understand. That's why I'm presenting this. And we can see this in actual videos. So I'm going to show you 2 videos, and I'm going to play them one by one. So the first video, which is being played at 4x speed, is one where a fractal robot is instructed to open a drawer and fetch a bag of chips from the drawer. So it's able to go and get these chips now. And even when there's an adversarial disturbance, one of our colleagues puts those chip bags back into the drawer. It is able to plan and put those bag of chips back on the shelf from here. So that gives you a sense of like the planning capabilities can be relatively good in these particular scenarios. Now let's take a look at a second example where the model is required to sort the blocks. This video is playing as 2x speed. So here, PAMI is required to sort the blocks. So it will move all the blocks of different colors to different corners. So you are watching this happen here. And now that the blocks have almost made it to their respective corners, we will find that there's an adversarial disturbance. And despite the adversarial disturbance, the model is able to replan and put the blocks back in the right corner. As you see, there was more adversarial disturbance, and the model is able to replan even after that. Okay, so this gives you a sense of how these long horizon goals can be met with language commands and action steps. And one interesting aspect that I mentioned about transfer is that when this model is trained on just a single robot, like taking the data from a single robot, the y-axis, what it shows is the accuracy, and the x-axis shows just what data the model is trained on. So when the model is trained, say, on just SACAN, the fractal robot affordances data, or just a language table environment data, or the task and motion planning data, then it gets lower accuracy. But when it is combined with the internet scale data mixes, it's able to get much higher accuracy. That is extremely promising in terms of the transfer that you get from internet scale data sets to robotic data sets, thus implying that you can really scale better by combining these data sets and co-training. Okay. Now we have seen some signs of multimodal reasoning, spatial reasoning, and challenges in spatial reasoning, and we have seen some examples of applying these models to applications in robotics. Next, we will see some applications in computer use, and much of this work on our side is unpublished. It's a bunch of collaborators at Meta. So what I'll be presenting is basics from peers in the community, which have shown some really promising results here. So if you look at agents for web and computer use, this is not a new area. There have been several benchmarks over the time. So recently it was presented that first there was MiniWob, which was there. Then there was WebShop. There was Mind2Web, another benchmark. Then there was Web Arena. More recently, there was another benchmark, C-Act. And then there have been a sequence of benchmarks like Visual Web Arena, C-Click, Mind2Web Live, and so on. So it's an area which has a lot of different benchmarks over time, where the environment gets increasingly complex and realistic, as well as the requirement is that the model acts more human-like and is only using vision and no other tools for planning. And there are several other papers that have tried to tackle this problem. So one of the key challenges in solving such problems is to get visual grounding in the correct formats. So in robotics, we kind of talked about the spatial reasoning problem and being able to understand relative distances. In computer use problems, a lot of the requirements come from being able to generalize across, say, desktop, mobile, and web environments, and then being able to handle input images of, say, different resolutions. Perhaps there will be different aspect ratios as well. And a lot of times, if the vision encoder is only taking a screenshot and then splitting it into, say, 4 blocks, or then getting the localization to be correct can be oftentimes challenging. So how do you get that aspect right has been a focus area for a lot of contemporary works. And our colleagues in present in a Ferret UI2 paper show that this is a problem that's solvable by providing detailed description of data sets. And in fact, they show that you can get almost universal user interface understanding across, say, iPhone and iPad, and even other screens by just constructing really detailed captions of these data sets. So this is an example where you're seeing a phone, and basically it is showing that all of these boxes and widgets and icons have basically been identified in the data set itself that they constructed, so it's easy for the model to understand them. This is another example where they're taking examples from, say, a MacBook or from Apple TV, and they're able to really show that each of these widgets and icons and even the OCR text is basically well understood in each of the conversation that the user is having with the model. Now, one of the interesting things that another paper, uGround, shows here is that it's not enough to just, like, say, understand widgets and icons. Oftentimes, these icons or buttons will have different meanings. So there might be different ways in which users express this. So like just labeling them is sometimes not quite enough. So they do another, they have another set of proposals in how these visual grounding tasks need more detailed data sets of what gets defined. And with that, they are able to show some promising results in a scenario where, say, you are trying to find, you're trying to buy a monitor and you want to be economical. They're able to show that if you have planning and grounding in the loop, then you are able to do these human-like operations and really click on the right coordinate. So you can get a vision-centric agent. And in fact, this style of work was actually released in one of the frontier models from Anthropic, where what you're seeing is, okay, we need to fill out, the model is asked to fill out a vendor request form from a specific company into, which can be either in the spreadsheet or in a search portal, and then it's supposed to verify the fields. And very promisingly, the model first comes up with a plan, and this is I'm giving screenshots of the demo that is presented, and then it's able to figure out, okay, no, I need to switch to another application. It finds the relative company or the workflow that it's supposed to go find, and then it's able to extract the right details to fill out the form. A lot of this means that the workflows become much easier to tackle. Now, this is still in early signs of what's possible, and the paper that I provided in supplementary reading of the dawn of GUI agents provides a very detailed benchmarking of this particular application, where they consider different domains like web search, workflows that you might do, or office productivity workflows, or video games. And not all of them are successful. In fact, like several of them still show failure cases in terms of outcome when you try to go and tackle these cases with computer use, which suggests that we still need to do a better job at one of the aspects of how we achieve these workflows. One interesting aspect that is really done well and understood is that we saw in robotics that we are doing some form of planning in PAMI, and then the model takes action, and then there is some language feedback that comes back. Very similar to that piece of work, here also we see that there is some form of planning that is happening in the model. If you look at the examples in the paper, and the errors that happen in planning might be that the model does not understand the instructions that are given to the model, or it doesn't understand at what state it is in the computer. Similarly, when it goes and takes action, it might not be able to take the correct action even when the plan is correct, because it can have visual grounding errors. You might not have enough precision to understand what's on the screen. And finally, you can have errors in the critic, where when you're looking at the screenshot of what the model has executed, you incorrectly assess those actions or computer state, which leads to wrong feedback on the loop, on the feedback loop side. So with that, I will actually conclude the talk and I think we have covered a few different areas today, which hopefully provides you with a broad understanding of what's possible with these models as they seamlessly reason across modalities. So a lot of the contemporary models, Gemini released last December, and then many models released this year have shown the capability to reason across modalities. We saw several examples where they can reason across interleaved sequences of image, text, audio, code, and so on. And in PAMI, we show that this abilities that you're getting from multimodal reasoning also transfers across robot and general visual language data sets. So you're able to get a single model that can like reason across, say, robotic environments as well as, say, internet scale data. We do have some work on the medical domain with MedPAM-M, and then PAMI, a similar follow-on work, combined action policies to build RTX. And then in computer use agents, which I did not cover in much detail today, we kind of saw the importance of visual grounding and planning, which also has very similar characteristics to what we saw in robotic workflows. And with that, I will conclude the talk.
Thank you, Aakanksha. Time for questions. I saw some in the chat.
I wasn't tracking the chat, so I actually will let you help me here a little bit.
Yeah, we can just let people speak up and ask the questions again. Does anyone online want to go first? Not anyone in the class? Yeah, why don't you speak up? Yeah.
Sure. Thank you so much for the talk. I was curious, you mentioned that there were huge bottlenecks on robotic data sets. And I was curious
Yes.
what the state of the art on generating these data sets were and why you couldn't just do it in simulation and kind of do it at large scale for pretty cheap costs.
That's a great comment. So yes, you can do it in simulation. There is always a simulation to real world gap that then you have to bridge. And I think a lot of the parallels can be drawn to self-driving cars, whereas a lot of the trajectories were collected, for example, so in self-driving cars come before the current excitement around robotic tasks. A lot of those trajectories were collected in simulation environments, but then you still have to do the work to do the sim to bridge that sim to real gap, because there will be unplanned interventions that happen and adversarial disturbances that happen in real world that you then have to have the model tackle.
I have one question. So if we imagine, if we divide the space of multimodal FM research into, say, 3 layers, right? One is at a very low level of perception. The other can be slightly higher level, say, action and event recognition. And the third is even higher level, like scene analysis and understanding. Where do you think, much of the future exciting research lies? Have we solved, for example, the problem at the lowest levels?
Okay, let me answer the question in another way, because I can answer that question, but I think I cannot give all the details for that. So I think the research is always exciting at all levels. I think the basic set of thing is that I think in perception there are still open problems to go solve. But oftentimes, if scale is the answer to those problems, then those won't get done in academic research. So if you're a researcher who's trying to solve them in on perception, you still have to work with smaller models. So in that one sense, I think it's more exciting to be able to understand, say, the higher levels of research if you're working with larger models. But there's a whole set of papers that I presented, like uGround or Ferret UI, which are still solving the perception-based problems on visual grounding before, say, you go tackle anything that is like at the planning level or the event level. Does that make sense?
Do you want me to read out questions from the chat?
Yes, please.
Okay, so there's one question. What is your take on smaller models, 3 to 10 billion parameters, for tasks like computer use or robotics versus very large models, 500 billion parameters? Do you think there's a place for smaller, specialized models and high quality data?
I mean, we're seeing that in real life right now. I mean, both like there's multiple startups that are going after small language models, and especially when you need an action loop, which needs to actuate in real time, and you saw that in PAMI. You do need a model that is basically fast enough for the taking the actions. So there's definitely room for that. Now, can you get all the capabilities out of it? That is a question that that will get answered as we see some of this work get tried out. But if you look at Pi Zero, which is one of my ex-colleagues from Google released from Physical Intelligence, their model, their paper suggests that like they are getting pretty good policies out of such models. So they don't have like the largest model. And another interesting example that just came out was from Edge Company, which is another startup that has released a model for computer use, and their models are extremely small as well. So I think that there is, anytime you have an action loop, you do have room for that. It might, I think the question of what capabilities just exist in the small versus the large model, we need to have better benchmarks to understand that part. I think a lot of the benchmarks that exist in the, so you asked me about research earlier and where the research is more exciting. I think a big aspect of answering these questions is having the right evaluation benchmarks before we can say, okay, this research is more exciting or less exciting. And a lot of that is happening, say, by every lab constructing their own evaluation benchmarks right now.
I'll get an easy question out of the way. Is MedPalm M available for use now?
That's a policy question. I'm not able to answer that. I don't think I have the details of what is available on cloud.
The next question is, in the multimodal reasoning model, are features from multiple modalities need to be aligned in the feature space?
What do you mean by aligned?
Can the person who asked this clarify?
Yeah, I mean aligned in, for example, a green box, and in the text and in the image, do they need to share the same, back to the same location in the feature domain, like that?
Yeah, I think what Yuan is asking, right, is, let us say it's a language within model, right? And there's the word green in the text, and there's a green colored object in the image. They embed. Are they embedding similar? Is that what you're asking?
I think that's a great question. So the short answer to your question is that if you look at Ferret UI paper, it is, and even the other paper that I presented, they are giving data sets that suggest that the model needs some indication on the green box and the text that says this is the green box. There is some indication that this is the same text, right? Like this is the same thing. So there needs to be something in that space. But then the vision encoder learns that. But your data set does have to say something to that effect.
I had a question on, you had mentioned as inputs like pixel space versus like 3D neural scene representation. And you had said that the state of the art right now, or what the community chose, is the pixel space. I was curious why that was, or if that's like long-term going to be the default input.
Actually, I don't think that question is settled at all in some ways. I think what I said was that in the open source, that's the model we have available. And for the closed source models, we have no details, right? For the open source ones, we do know, so that's what I presented. But there are several startups that are going after physical world understanding, not one. There's like multiple startups going after that. So I think the key question that is worth asking is, what do the 3D representations buy you in terms of the task understanding or image understanding and so on? And I think the kind of problems where I showed you benchmarks or demonstrations, it didn't seem to make a difference. So that's why, like all the examples that I presented in this particular presentation. However, if you're deploying things in real world, imagine self-driving and others, then you might do, you will need some 3D scene understanding, right? So I think it comes down to what is the domain space in which, or application space in which these models get deployed, and what are the requirements in some ways. That's where I say the evaluation benchmarks are not capturing everything.
Here's another question. Do we train different parts? Well, I'll rephrase it. Is it better to train different parts of a multimodal model, for example, vision encoder and LLM, separately or together? The question about early versus late fusion.
Okay. I'm actually going to refer you to the papers that you should read on this one. I think the community is still deciding in open source what is the right thing to do. But I think we have answers. So Llama 3 went with, okay, train the vision encoder and then have the LLM, but they actually froze the LLM when they combined those two. Pixtral went with vision encoder trained separately and projected to the language model, and then they are basically adapting there, and you will see Lava models do very similarly. So that's the open source community's answer. I think there is probably more interesting works like Chameleon from FAIR, which show that there's promises to be had from solving things where you combine modalities a little bit early. So, I mean, I think this is a research question where there are several papers and benchmarks this year. So we will see what ends up being the final set of things. I think one comment I want to offer is that oftentimes, given that an application space you are building on top of the models, the more modular they are, the easier they are easier it is to build on top of them. But it always helps to have like these results. So I think this is a research question that multiple labs are going after right now.
Okay, here's another. What's your take on VLMs with or without an explicit vision encoder? Adapt showed promise with their new style, which has no vision encoder.
So I think the whole patchifying the image and then feeding it into the language model, given that they've showed promise, that's completely doable. I think there's not as many results available in open source community other than that Fuyu model. There is one paper, but I think there is more scientific published research that's needed in this space. So my take is that it's whether it's better or worse, we need the right set of benchmarks to compare them apples to apples.
There's another nice question, which is, are there any specific criteria or security measures in place for data collection, particularly for web-based tasks?
Yes. So I think, I mean, given that this talk was mostly around just understanding what the capabilities are available from these models, I didn't put that slide in, but there's a lot of work that goes on in each lab to really make sure that the data that's collected is done so responsibly. And there's a good amount of effort, and I would say for just about every single lab in ensuring that just the data collection stage follows a certain set of protocols in just what is okay and what is not okay, and getting legal approvals in place for every single data set, so that based on whatever set of policies the lab is following. So it's not a decision that is made at an individual level. It is essentially a policy decision that is made with a lot of thought and care. And I can say that for several places that I've worked. I don't want to get into the pigeonhole of specific criteria because that starts to reflect on specific workplaces. But yeah, I can point you to papers there of how the responsible deployment is done or data collection is done.
Here's another question. Is there any intuition as to why a larger model can minimize catastrophic forgetting? Not sure if this is specific to multimodal.
I think the larger model has just a bigger parameter space, so it can basically ingest more data and still not forget the earlier data. So it in that sense, it basically has more capacity overall, which is a very simple answer, but like it's actually true if you evaluate these models.
Any final questions? Not, let's thank Aakanksha. Well, there's just one more. Sorry.
Okay, yeah.
The last one. Can you expand a bit on the SOTA on handling variable image resolutions and specifically large resolution images? Sampler, perceiver, dialing, etc. Is it a worry that if you compress or limit the number of tokens for each image, then fine-grained information may be lost? I work in this space, and this is specifically an issue for sequences of frames, like a history of screenshots and actions.
Oh, I completely empathize with you that is a challenge to solve for. The only answer I can really give you right now is that I think so there is two answers to the question that you're asking. One is that so basically there's the variable. I think you asked the question from variable image resolution and large resolution of images. I think that aspect, at least from vision encoder side, has much more prior research. I think the getting the perception to be reliably correct. When you say variable image resolution, I think there is a fundamental assumption you're making is that the large resolution images will be kind of compressed or tiled in some interesting ways. But I think there is some interesting results this year, both from the paper that is released from Apple and from Mistral, so the Pixtral model and the Ferret UI model, that kind of work around those and still show very promising precision results. Now, I will say that if you made these large resolution images not of screen like the computer use, so that you have a computer screenshot, if you made them a medical image, for example, the amount of localization you need to get would be at a very different level. So it is a little bit application specific to get the right solution in place sometimes. But I think there were some promising answers that the papers this year have released, and I think there needs to be some apples to apples comparison of like which one is the thing that we should go after if we were to compare on exactly the same benchmarks. The reason I didn't give you a very clear-cut answer, that is the answer, is because or like this is the state of the art, is because they don't compare on the same benchmarks. So it's like very hard for me to answer that, right? And I can't answer what is cooking on our side. At least
okay. This was very helpful. So with that, let's thank Aakanksha once more for a wonderful talk.
Thank you all again. It was great giving a talk.